everybody. I am in the math department at University of Nebraska, trying to eventually get a PhD in math. And yeah, so it's kind of annoying. When I tell people I'm studying math, I get a lot of like, oh, whoa. And then, like, I was really bad at long division when I took math in high school. So it's very alienating. And so, you know, a lot of people think the solution is to, you know, give some talk about why math is applied to something and why it's important to this thing you care about. But I don't know, I'm just sick of it. So instead I'm gonna tell you why insects are better than you at math. So first of all, when did you learn to count? Before you look, just guess. We'll say maybe, what, maybe 3, 4 years old? No, you're wrong. The idea is I'm going to tell you you're wrong a lot, so just go with it. So about 3 to 4 days old, human babies start to learn to count. How do we know that? Tests like this. So we set up baby in front of the television screen, and they're kind of into the whole 2-dot thing. They think it's pretty cool. All right, there's 2 dots. And after a while, they get a little bored with the 2 dots. They see it's moving, but eh. So they start to drift off, stop paying attention. We've seen the 2 dots already. And then, oh shit, there's 3 dots. That's interesting. And they start looking for a while again, and then they get used to that. And then 2 dots again, they start looking again. So the idea is they can kind of gauge their eye movement and just see how close of attention they're paying, and they can at least tell that they know the difference between, say, 2 and 3. And this is a process called subitizing, which is basically how we all count. So the idea is we just group things into small numbers. We can usually do up to about 7 through subitizing, where we just visually see it and we know. So like, think about when you look at dice. You instantly know what number is on there. You don't have to count the dots individually. So roughly about 3 to 4 days old, babies already have this ability, which is really impressive, right? Right? Wrong. All right, so ants have been counting for 150 million, since 150 million years ago. There we go. Sweet sound effects. I met with Michael Bay earlier to put this together. So, yeah, about since 150 million BCE, ants have been counting. And now you might have the ridiculous question, how do we know ants can count? Same way we answer most difficult questions in life, ant stilts. So the idea is, we set up ants in a little home, and we set up food far away from the home. And then ants go and get the food, and when they get to the food, some lucky ants get left alone, like the green guy there. And then some other really unlucky ants will pick them up with nice little tweezers and chop off their legs at some point. And so those guys get stumps. And then some really lucky ants, we take them and we give them super long legs, so they're massive. And so what we see is the normal ants get back to their home just like normal. The stump ants don't make it all the way there, and then they just stop. And then the stilt ants just breeze right on by. And we know they're not just showing off their badass new stilt legs to the ladies, because they're all ladies, so they don't need to compensate. So they happen to be counting their steps, is what we can infer from this. So primates have been counting for roughly 30 million years. And humans, well, our first evidence of humans counting is about 18,000 BCE. Then you might say, humans are primates, why can't we kind of put it in this number? That would throw off the theme of my talk, which is that insects are better counting and math than you. So we're going to go with it. If Hillary Clinton can pretend her Iraq war vote was a mistake, and that she regrets it, I can do this. To be fair, she didn't know it would be unpopular a decade later. So now we got these Shingo bones. This is our first evidence of humans counting. We know this isn't just scratches. We know these are very specific tallies. One of the main reasons we know this is that there's actually a chain of prime numbers here. So it's clear that we already knew the importance of prime numbers pretty much from the beginning of our counting and mathematics. So now I need to check and see if you even remember what prime numbers are. Which, if you don't remember what prime numbers are, I'm upset at you because you missed a fantastic talk last month from Robert. Yeah, cheer for Robert. He's awesome. And so I'm assuming if you missed that talk, you're too lazy to look it up yourself, so I'm just going to Google it for you. So prime number is a whole number greater than 1, whose only two number factors are 1 in itself. The first two prime numbers are 2, 5, 7, 11, 13, 17, 19, 23, and 29. So the idea is what divides 5 when you want to get a whole number out. And 1 works, 5 works, 2, 3, 4, none of those work. So that would be a prime number. You're welcome for Googling that. So we knew prime numbers were important from early on. And we actually have contrived these really complicated methods to find prime numbers because they're super important to us. So this is something called the sieve of Eratosthenes. And the idea is we first take the number 2, which we just sort of know essentially by definition that that's prime. And so we save that as a prime number. So we save it here. There. Oh, wait. I'm going to tell you you're wrong again in a minute. Nope. Nope. Well, there's an animation there. Oh, there it goes. All right, so we save the number 2, and then we count up by 2 each time, and throw all of those numbers out. We know those aren't prime numbers because they're divided by 2. Then we do the same with 3. We save it, we count up by 3, we throw all of those out. Then we go to 5, because that's the next number that's not already thrown out in some way. We save that, then we go to the next number, which is 7. 11, 13, and eventually there's no numbers left to throw out. Every time we count up by a certain amount of numbers, everything's already been thrown out, and so everything left is a prime number. And so this was sort of our initial method for finding prime numbers, and now we have more advanced ways to do that, but most of those are still prime number sieves. They're still sort of essentially this concept. So that's still sort of the way we do it. And of course prime numbers are super important. We use those, for example, to protect your dick pics from, I don't know, Russian hackers. And yeah, so us mathematicians are working hard on that. But humans were not the first to discover that prime numbers could protect your dick pics and other things. Cicadas use prime numbers not to die. So the idea is a lot of cicadas use prime numbers. They live underground most of their lives. They just eat lots of food. Then they eventually pop out of the ground, have some sex, and then they die. Which sounds kind of awesome. You get to skip all the pain and disappointment that comes after. And the idea is a lot of them actually emerge in synchronized periods of either 13 or 17 years. So every 13 years you'll see a particular species. And so it turns out cicadas are actually a prime number sieve, just like the one you just saw. And so the way that works, I'm going to do a mathematical model that humans can understand. Lots of pictures. We got some cicadas. And then the predators show up. And of course, predators do what they do best. They kill a bunch of the nice little guys. So hopefully they don't kill any of your favorites. Cross your fingers.
Oh gosh,
I like that one. Yeah, I know. It's like the red wedding. All right, so we lose some cicadas. From dust they came, into dust they shall return. And now the rest of the cicadas are going to go underground, right? That's what they do. So in that time, the predators got a lot of nutrients. They can do a lot of replicating, so they start popping out babies. Like predators sometimes do. So after they get busy, no cicadas show up for another 13 years. So if that's their primary food source, we're going to start losing a lot of the predators. Again, cross your fingers for your favorites. All right, that was a lot. 13 years is a long time if that was your primary food source. Well, now the cicadas are back. And of course they did some replicating. We know they were having sex before they went underground. So now they're popping out some babies. Literally popping out some babies. And then the predators do their thing. They're going to kill a few, but the numbers have dwindled, as you can see. So they're going to kill a lot less than before. So we lose some, and then we go back underground again. And the predators are going to mate a little bit. And again, 13 years is a really long time to go. So the idea is, and by the way, the cicadas are really happy about what just happened. Can't miss that part. All right, so the idea is, if the cicadas were going underground every, say, 4 years, and say our predator, the wasp, say had a life cycle of 2 years, well then every other year they're going to get a huge boost in their population because they got to chow down on cicadas. So if you have a periodic predator, you're pretty safe if you have a prime number because none of those numbers divide your prime number. But in addition, predators just can't use it as their main food source because it's so rare. It's only every 13 or 17 years. And so here's the real mathematical model. Here's the results from it. Well, one of them. There's actually a lot. And so you'll notice there's a lot of numbers here. These are all different life cycles they try out. And of course they incorporate death and predators into it. And you'll notice everything is right along this line. They're all dead, except for the 13-year-old population, or 13-year-old cycle population, the 17 and the 11, which are all prime numbers. So they actually behave as a seed for prime numbers. All right, so we're going to change course a little bit. We're going to talk about Scottish kids. So the SQA, if you haven't heard about it, is sort of like the SAT, but in Scotland. And so they take this test that hopefully gets them into college. And last year there was a bunch of Facebook posts about this, at least for me. I don't know, I run in weird circles. But people were upset about this question because they said it was too hard. I guess it made a bunch of Scottish kids cry. So the idea is this. I'll read it to you because it's a little small. A crocodile is stalking prey located 20 meters further upstream on the opposite bank of a river. Crocodiles travel at different speeds on land and in water. The time taken for the crocodile to reach its prey can be minimized if it swims to a particular point P. There's our point P. X meters upstream, so there's X meters right there. On the other side of the river, as shown in the diagram. The time taken T measured in length of seconds is given by this equation here, which is 5 times square root 36 plus x squared, plus 4 times 20 minus x. So the idea is this. We use the Pythagorean theorem and multiply it by essentially a speed to get this distance, just the hypotenuse of a triangle, right? Length and distance. And then this is the straight line distance on the land, which is going to be 20 minus x. It's however much ground they didn't already cover by going this x many meters. And so the first two questions are simple. I think probably the Scottish kids got these to calculate the time taken if the crocodile does not travel on land. Well, that's just going to be a hypotenuse of a triangle directly to the zebra where x is 20 feet, which means 20 minus 20 is 0, and you just get this piece right here. And then the other idea is calculate the time taken if the crocodile swims the shortest distance possible, which means it's swimming directly across, no triangle at all. And what was that? Yeah, it's 6 meters, and then directly 20 meters on land. And the idea is because the speed is so similar but not the same, both in water and on land, it's actually faster on land, but not by that much. There's actually an optimal distance somewhere between going directly to the zebra and going across into the zebra, somewhere in between. And so the third question is, between these two extremes, there's one value x, which minimizes the time taken. Find this value of x and calculate the minimum possible time. And so the solution's simple. I'll take it through take you through it nice and slow, since you're not an insect. All right, so take the derivative, set it equal to 0, subtract, multiply by the denominator, square it, subtract, divide, take the square root of x equals 8, plug in the original time equation, you get the optimal 9.8 seconds. So hopefully you kept up. And if not, you should be ashamed of yourself because ants do this math on the reg. So ants effectively do this exact thing. And so this is a experiment where they set up 2 different places where ants could run. And so there's a surface here in this rectangle, the second surface here in this rectangle. And the idea is that the food is some diagonal distance away. And so there's actually going to be some optimal angle or optimal distance x where the ants essentially cross through after traveling in 2 straight lines where they can get to the food the fastest. And so we can calculate this mathematically once we know what speed they can travel on each of these 2 surfaces. And it turns out that every time we calculate this and then set off ants to do this exact same thing, they happen to go the optimal route. So somehow they're actually doing this calculation. So the idea here is they set up some sort of like astroturf and then some nice smooth surface where they could go much faster. And they just always pick the optimal angle. So, I mean, what does this mean exactly? I mean, we don't really understand how they're doing it. The assumption is it's something numerical. Numerical analysis mathematics is basically a way where we approximate when we can't get exact solutions. And presumably the ants are doing something like this. It's some sort of trial and error thing where they're trying out a couple paths and then they somehow start to converge on a path that's optimal. And in the same way, in a bigger scale, all of this mathematics that we see insects doing is also a trial and error basis, but essentially through natural selection, which in fact does a lot of optimization. And so this is the exact same process that created the structure of our own brain, the machinery that allows us to do mathematics. And so yeah, we got the same power as these stupid little ants and this stupid grasshopper. You look stupid. So, the next time you have an opportunity to do math, at least if you're kind of super competitive like I am, I don't know, I would just encourage you to think about, do you really want to get shown up by an insect? That's it.
Hey.